Hello everyone and welcome to 10th session of 3D Thursdays webinar series. I'm thrilled to have you with us today as we dive into exciting world of additive manufacturing. As many of you know, additive manufacturing or 3D printing is revolutionizing various industries, and our topic for today's session is holistic quality assurance in metal additive manufacturing process chain. So let's discover how digitized measurement workflows are enhancing the reliability and performance of metal additive manufacturing across industries such as medical, aerospace, space, or automotive sectors. From powder to finished part, cutting edge technologies like optical scanning, X-ray inspection, electron microscopy are ensuring consistent quality, enabling faster and quick prototyping, customized components, and sustainable production practices. In this session, we'll delve into how these advanced measurement solutions are driving the innovation and improving the traceability and supporting the industrial scale adoption of metal AI. So we encourage an interactive session here. So please feel free to ask questions. A dedicated question answer session will be there at the end of the presentation, but you can submit your questions using the chat window here. To ensure everyone has a chance to participate, we might club the questions, similar questions together. We will also address as many as time permits, so don't hesitate to share your thoughts. And lastly, please note that this webinar is being recorded. So by participating, you consent to the recording being shared for educational purposes. So let us introduce our speakers for today's session. First, we have Mr. Manoj K. Sundaram, Head of Business Development IQS at Zeiss India, Bangalore Private Limited. Mr. Manoj is a business development and customer segment head for Industrial Quality Solutions division at Zeiss India. He's adept at presenting technologies, understanding market requirements, and configuring turnkey solutions using extensive array of surface, form, dimensional, and X-ray metrology equipment offered by Zeiss. With a background of electronics and communication engineering and over 2 decades of experience in precision metrology across various industries, he is well positioned to deliver impactful solutions in the engineering space. Joining him is Mr. Palaniappan Muthaiah, Business Development Manager, Microscopes at Zeiss India Private Limited. Mr. Palaniappan is a Business Development Manager for Microscopes in the Industrial Quality Solutions Division, a seasoned technocrat with deep expertise in varied industrial application, and he understands customer needs and guides them in adopting cost-effective solutions using Zeiss' extensive range of microscopy equipment. With a background in mechanical engineering and over 3 decades of industrial experience, especially in microscopy and specialized component cleanliness management, he brings valuable insight into quality assurance processes. Together, they will guide us through how digitized measurement workflows are transforming metal additive manufacturing from powder to the part. So let's warmly welcome Mr. Manoj and Palaniappan as they lead us through today's presentation. Over to you, Manoj.
Thank you. Thank you, Suhaib. Thank you so much for the nice introduction to the company and both of us. Thank you, friends. I see a lot of you, and I hope the next 40-50 minutes, what we would present an array of solutions would be useful to you in the space of additive. We would, as Mr. Suhaib was mentioning, we would like to have it as interactive as possible. And before I start, I would like to thank Wipro Additive for giving us opportunity, and for Suhaib to really thank you, Suhaib, really for putting us and giving us this platform. So let me jump into the slides. We do have a lot of them, and we would like to present it in as far as possible in a sequential way, which is easily understandable. We will get there. Okay, good. Right. So good afternoon, nice afternoon, and here I am. I'll be presenting on the quality assurance solution for additive manufacturing. there will be a lot of slides, and we want to give you a kind of a headline approach into a lot of solutions. Yes, not necessarily that our explanation in all the slides would be adequate, and you may probably need to follow up with us. We are open to it, we are accessible, and we are based out of Bangalore, and we can always interact. So that is a overarching topic. We will mostly focus on these two topics when it comes to metal additive. We're focusing only on metal, basically, into powder bed fusion and DED. These are the two areas where we will most of our solutions will focus on. Carl Zeiss is a German firm, 178 years of existence, and we have discovered and helped a lot of patents and developments around the world, including lenses, which we are quite famous for, which you might see in some of the consumer electronic stands. So we represent what is called industrial quality solutions, and we are very well known for in this space with respect to the CMMs, which you see in the third column. So we are in the industry for CMMs for about 4 decades, 4.5 decades or so, having given a lot of solutions in the auto component and aerospace industry. Today, with the development and our existence in India, we are now split into a lot of verticals, as you can see, industrial microscopy and X-ray. These two verticals, column number 4 and 5, there are quite a few solutions which help the industry, particularly the additive industry. So today's focus would be on column number 4 and 5, and we will touch upon software and optical solutions also as we move along. Our solution space is divided into hardware, which you see on the top line, CMMs, optical systems, X-ray or CT systems, industrial microscopy. Also, we have the middle line, which is a host of software tools, CMM softwares for optical inspection techniques, where you capture millions of points, X-ray software, where you capture a lot of voxels, not pixels, but voxels, because it's a 3D element. And then again, in the industrial microscopy, we capture a lot of data points. So all this have been combined into a single usable software called a Zeiss Quality Suite. So which is, the software platform is also one of our strengths as we move on. We have also moved a little bit into using AI in many of the techniques, many of the software tools, what we provide you, particularly into X-ray, because not everything in today's industry, not everything can be manually ascertained, manually controlled, can have a manual interference. There is a growing need for automated inspection, artificial intelligence based inspection, and we do have the solutions embedded into our topics. Okay, now to come into today's topic, additive manufacturing, we realized about 7-8 years back that we do have a set of solutions. The microscope, CMM tools and software is able to really give a workflow around the manufacturing processes of additive. This is our view of how the additive workflow moves on from 1 to 5 rather. So number 1 will be powder, and when you start with the powder and characterization, then you print it, and then you want to do some heat treatment and warping, and then so on, studies around it. Then probably the most important topic today would be to look at the defect and the inner structure inspection. And then, yes, coupled with it, the metallurgical topics are quite important to understand how the material is behaving from a fundamental point of view. That is number 4. And then when you want to ship the part to a customer, yes, you need to do some post-processing and then ensure the surface dimension qualities are right and as per the drawing. This is achieved by the solutions at the bottom, like microscopy, scanning, 3D scanning, X-ray, and so on. So this will be the 5 samples, or what you call the sample locations along the process, what we will be moving. These are the tools what we have. uh, CMMs, optical scanners, X-ray systems, nano X-ray, or we call it a XRM systems, light microscopes, and electron microscopes. Each one of them needs a different skill, needs a different software. They throw out a different variety of data, and all these help you combine together to help you understand how good is your quality. Just for you to understand a rough price point, just to understand, a CMM would be in the range of around anywhere between 40 to 50 lakhs for an additive topic. A 3D scanner would be in a similar range. A X-ray CT would be in the range of around 6 to 10 crores, depending on the configuration. A micro CT would be in the range of around 10 crores or so. Light microscopes in the range of around 30, 40 lakhs. Electron microscopes start at around 2.5 crores. So this is the kind of tools and the cost per se involved. Fortunately, most of these tools are available at our quality centers in Bangalore. If you say at Bomasandra, we have most of these tools available, and most of the solutions what we will discuss are available here for you to come, discuss, and work with us. Now, how we got into additive is an interesting story. As you see in the slide, this is a laboratory what we have set up at Oak Ridge National Laboratory in the USA, which was a hub for additive manufacturing processes. So here is where we learned a lot of techniques, tools, and we fine-tuned our knowledge pool. And this is one example where we worked with Porsche to make an additively manufactured piston. And the alloy and the process is mentioned there. There was a 10% weight reduction achieved. There were integrated cooling ducts for the piston to cool down, and there was a 30 horsepower boost in performance. So this was a proof of concept activity which happened. It's a short video which I would play now, and let us go through this video. But I think the audio may not be coming, or let me see that. Yeah. This video would encompass all our solutions in a very short span for you to look at. Is it okay, Barney? Okay. Right. So I think you would have got a fair idea of what are we trying to discuss in this seminar, a complete workflow. So we will, as we go through it, this is our office at Bomasandra, and we have similar facilities all around the country. We have our QEC center where we welcome you to look at all these technologies. And now, diving into the seminar, I would like to invite Mr. Palaniappan Muthaiah, who will present on the microscopy techniques, and he will take on. Parani, would you like to take on?
Yeah. Thanks, Manoj and Soeb and Wipro team. Thanks for this opportunity. And from my side, we welcome all of you for this session. And I would be glad to take you through the process related to the raw material and characterization through the microscopy techniques. The slide where you can see is related to the material. What are the challenges the industry is facing in the complete process line, I would say. So we had broken down the complete process into material design, layout, process, and post processing, as well as the final part inspection. And our topic or my role specifically will be on the material analysis and final part inspection. So when it comes to the modern 3D printing process, what you would like to do is a comparison with the properties of conventional manufacturing. For example, normal forge or cast material, how the 3D printed part will be comparable, and what kind of failure mechanisms and how we can address these failure mechanisms to be taken up. And to be specific on non-destructive characterization is a new technology. What Manoj, previous slide, please. Yeah. And with the 3D non-destructive measurements, we have X-ray systems on both metrology front and microscopy front we have. And we can also optimize these complete process along with the CAD models. If there is no CAD models, also we can do the Zeiss. ZRE is the software where we can do the reverse engineering and we can analyze the products. Yeah, next slide, please. When it comes to the microscopy topic, I would like to break it down to three equipments. One is the optical or light or confocal microscope, where we talk about the incoming raw material, that is a powder qualification with respect to the shape and size. For example, there is an inconsistency in the quality of the raw material what you procure. Your entire process, the timeline, the money spent is going to be wasted. So it is better to have the incoming quality check where these microscopy can be ready to use. And the next step is the scanning electron microscope. When we talk about the shape and size of the particles, that is the raw materials, it is also evident that the required chemical composition of these analysis is in place to ensure that these electron microscopes can be used. And post-printing process, there is a technique called EBSD. With that, we will able to see how the print pattern and how it relates to the tensile strength of the component is achieved. And we also have this correlative analysis. There is a specific slide which I will describe. This is nothing but interconnecting the data sets of different equipments to understand the same region of interest for a different techniques. And the third one is the non-destructive testing method, which is called X-ray microscope, where you can look into the without post printing of the parts, without cut opening or without sectioning the sample, we will able to dive or delve into the detail with respect to the voids, porosity, or material characterization, binder materials, etc., etc. Yeah, next slide, please. This is the complete array where you can see from the micrometer to nanometer scale. We have different range of equipments. Not only the different range of equipment, these equipments can talk to each other. That is called as a correlative microscope. From the external dimensions to the cross-section samples, and you can also do the sectioning or cross-sectioning of the sample and remove the subsurface defect with inside an SEM. That is called as a crossbeam or FIPSM, focused ion beam SEM, which is there in the last image of this slide. Yes, next slide, please. Yeah, next slide. When it comes to the material, as I said, the powder characterization study is very important, and we can use two different equipments. One is for the quicker classification of the understanding of the shape and size and morphology. When I say shape, morphology also comes into the picture. You can do the grading with the help of image analysis software. We can easily quantify what is the size of the particles, what is the shape of these particles with the light microscope. And if at all you need to understand the chemical composition, for example, the second image on the right top is having a chemical name as ALSI10. Whether this ALSI10 described by the supplier is there or not, we can also subject it to the SCM with the EDS. EDS is nothing but energy dispersive spectroscopy, where we can understand the chemical composition in a quantitative method, not the not quantitative, in a qualitative method. We'll be able to understand. In SCM further down, we can also get to know the surface morphology. In a light microscope, it will be a 2D image, whereas in SCM, we can also look at the 3D surface characters of the particles. This will help in the printing process, how the binding integration will take place, whether will be agglomeration or there will be a voids when you do the printing process. To evaluate those parameters, these data sets will help. Yeah. Next slide, please. Yeah, on the SCM earlier slide, we had seen the particles as it is, and we can also do the with the help of FIPSM, we can remove the surface and we can go deep into the individual particle. The first one is the SCM overview image of a particle. And if you see high dense and low dense materials, and high dense materials, if you want to understand the chemical composition, you can narrow it down to the particular particle. And once we go into the higher magnification, and we can see the voids, and there will be certain inclusions of the voids. If you want to get into it, we can, with the use of focused ion beam, we can do the surface removal, that is milling of the material, and then we can do the imaging and EDS characterization. So this will clearly guide you not only the surface level information inside the particle, if there are any contamination buried in, still then we will able to analyze and understand. Yeah. Now comes to the design and layout topic. Yeah, there is a video. Here you can see this is from the X-ray microscope. This is a finished component, and the prospect want to understand post printing what is there inside the material. Is there everything intact? And we could be able to identify unwanted material, which is called as a contamination present in the system. Yeah, you will come to know shortly. Post acquiring the 3D image, you can slice and dice the data. Now you can able to identify the contamination or unburnt material, I would say. This is in the 50 micron range. Once it has been identified in a XRM, we can also do the chemical composition analysis with the help of SEM with EDS in this process. So not only on the...
I just want to add, Parani, that these are not animations. These are real-time data which has been taken out of our equipment. Yeah. Yeah, please continue, Parani.
Yeah, we can go to this.
Next slide. Okay. Right. Yeah.
So the unmelted region, the one which we saw in the XRM, we can identify the location, that is basically the coordinates, and these coordinates are fed into the FIPSM along with the sample transfer. The sample holders will be common, so The XRM coordinate references are understood by the FIPSM. Then FIPSM with the laser faster milling and then fib milling, we will able to reach out the buried section of this unmelted particle, and then we will able to do the measurements in terms of dimensional or chemical composition also. So this we call it as a correlative workflow between the light microscope, electron microscope, XRM, and FIPSM. Yeah.
Okay.
Next slide. Yeah. Here we talk about the print pattern, scan direction. On the right hand side, you can see two different images. These are from the light microscope images. Post printing, the component will be made into cut section small. It's a traditional sample preparation process, cutting, mounting, grinding, and polishing. After etching, we will able to see this track direction and the track distance. This will help you to control the speed of the printing, thickness of the layer to be printed, how effectively you can avoid the voids or porosities in your printing process. This is very simple, direct go to answer with the optical microscope. Yeah. Next slide, please. Here you can see the width of the laser track or track distance, and you can also look at the voids if there is any unburnt material. On the right hand side, the side view laser fronts, you can see the black marks. These are unburnt materials. This can be easily identified with the light microscope itself. Not an expensive solution, but this will give you to improve the process in the printing of the parts. Next slide. Yeah. And with the help of image analysis software, we can also do the quantification of the pores and voids. Here we are trying to give you two different process parameter. On the left, you can see this is at 1.5 joules per centimeter, the printing process, where you can see the lot of voids are being present. When you increase the track energy from 1.5 to 3, the voids are reduced to a larger extent. So this kind of quick in at site or at lab analysis will help you to improvise the process parameters so that the rejection rates are less, or it leads to the lesser liability, I would say, at the end of it. Yeah. With the image analysis software, we can quantify the voids, number of voids, area of voids, etc., etc. Yeah. Next slide, please.
Yeah.
And this is again coming back to the X-ray microscope. On the finished parts, for example, I don't want to cross section, but still I want to understand the porosity. Still, the X-ray will penetrate through the component, and it is similar to what we have in medical CT. In medical CT, the patient is idle, the source and receiver will be rotating. In this case, the component will rotate, the source and receiver will be at the stationary point, and we will able to get the number of 2D images from the component, and with the help of software, we will able to identify the high dense and low dense material. Not only the identification of the material, we can also do the measurement of this contamination or the voids present in the component. This will help to improve again the process parameters in the printing.
Yeah, I just want to emphasize, Parani, that for the these are all internal images of the printed part. You are not doing a destructive check. You are doing a non-destructive imaging.
And this is the one technique used in the electron microscope. We call it as a EBSD, electron backscatter diffraction technique. How it will help is, it will identify or help you to understand the lattice pattern of the grain structure during the printing process and the heat treatment cycle, whether these printed materials are properly formed during the heat treatment process, whether the orientation of the grain formation is happening in the same direction so that the required tensile strength is being achieved or not. So this is one accessory used in a attached into an SCM, where thereby you can able to get this kind of grain pattern or lattice information, we can say. Yeah. Next slide, please.
Yeah.
This is again the correlative microscope, which I told about, the HRM and FIPSM kind of thing. I think there is a video over it, Manoj.
Okay. Okay.
I think there is no video. So the
There's
first
no
image
video.
is the XRM scan part, and the second image is the identifying the contamination present in the system, and the third system is the quantification of the contamination with respect to the EDS technique. So XRM, light microscope, CT, XRM, and SCM can be clubbed together for the same component for the same region of location without disturbing the sample to analyze. And here you can see the number of slices as 80392211500. So the XRM data is basically built of more than 1,000 slices. So at which slice these informations are available, that means at which location you have this contamination or voids, so that precisely you can go and do the cross beam application and get this EDS analysis done without compromising any information on the samples.
Apparently, just a question. Is this the print slice number, 3D print slice number, or is it the XRM
XRM slice number.
slice? Okay, it's the XRM
So,
slice. Okay.
I
Because
think with
XRM, yeah.
Param software, we will able to integrate the print slice number also. But this data represent here is the XRM slice information.
Right.
And we can see that at 1.7 millimeter, just go back, at 1.7 millimeter depth. So precisely the focused ion beam can be used to remove the material up to 1.7 millimeter. When we do the manual sample preparation, we are introducing the artifacts, or by improper sectioning, we may lose the contamination. In this case, precisely we can go to up to 1.7 millimeter depth for material removal. Then we will able to identify the inclusion, and we can do the analysis, imaging. When I say analysis, imaging and chemical composition analysis. Yeah. So this is again another example of the correlative workflow. On the left hand side, this is a prepared sample. You can acquire the image from the light microscope. Due to the limitation of the 2D image, you will not able to go have the in-depth understanding of the sample. Then the same can be analyzed in the computed tomography or XRM. Then the same location can be used for the FIPSM for removal of material up to a particular depth. Then we can do the chemical composition. So these equipments can talk to each other to understand the region of interest of the sample when it is being placed in a different equipment. This means without losing a lot of time, without losing the information, you are reworking, or you are working on the same sample on same region of interest at different equipments. With accuracy of 1 micron, we can say it is possible to achieve. Yeah. Next slide, please. This is again another example of the correlative. So we identify a defect in an XRM, and on the FIPSM, we do the material removal and we do the imaging. Post imaging, the right hand side bottom image is the SCM image, and on the left hand side, the 4 colored images are the chemical composition, or we say chemical mapping of the contaminant, where you can see ferrous, manganese, chromium, and copper is having presence in the aluminum printed part. So how come there's a contaminant having this composition present in the aluminum print part? So it is easy for us to narrow down which are the sources from where this contamination may come from, whether from the part of machinery or airborne contamination, or from the raw material, contaminated raw material. This will help to identify the root cause and to work on eliminating it during the production process. Yeah, next slide. And final part inspection, post processing. Yeah, not only on the powder characterization, defect identification of voids, pores, and EDS analysis, we can also do a non-contact surface roughness analysis. When we have the 3D printed parts, obviously this is something similar to the matte finish you will have the surface. And depending on the applications, you need to have the roughness parameters to be maintained. So how you will analyze the roughness parameters? Normally in metrology, it will be a contact type. That means probe will travel on the surface, the crust and trough are taken and the profile is analyzed, then you will get it. Whereas on the 3D printed part, the surface will be rough. So the probe travel will be limited. So in this case, we can also have a non-contact surface roughness measurements, not only for the profile and the area. For area also we can do. So this can be done with both XRM information as well as light microscopy. When we talk about the light microscope, here we use a technology called confocal technology. This will help you to acquire the Z-axis images at a nanometer level. The slice thicknesses are nanometer level. Then with the help of software, we construct the 3D data. From the 3D data, we will able to analyze the soft. With the help of software, we will able to do all the roughness parameters with respect to the standards. Yeah, next slide. Yeah, on the left, it is a 3D printed part, and on the right, you can see even though it is a cylindrical, after acquiring the non-contact type image, with the help of software, we can flatten the profile and we can do the roughness characterization study. Irrespective of the shape of the component, we will able to do this analysis with the help of software. Yeah. And this is a comparison between the XRM, which is a non-destructive method, and the confocal, where you do the cross-section or the surface level information. You can see the parameters as per the ISO 25178, the surface parameters, different parameters, and here we are trying to do the comparison of the data sets from both XRM and confocal, and where you can see it is very close. So it's not necessary that you need to have a X-ray microscope to do this analysis. With a typically around 200,000 euros, you will get a confocal. With that also, we will be able to do the roughness parameter analysis. Yeah, next slide. This is again the surface of the printed part, external and internal. Again, the surface parameters with respect to the standards with both the equipments. Yeah, next slide. And with respect to the X-ray microscope, it is not only the non-destructive imaging for the identification of defects or identification of pores or voids, etc. We can also look at the aspect ratio of the particle size and particle diameter. This will help you to improve the print parameters on your printing machine. Yeah. This is again the same topic with
yeah. Okay, I'll move on.
Yeah. I think on the microscopy front, these are the applications, and we have dealt with a few applications with the Indian customers on many occasions, and we would be glad to help the team here if they need any assistance. We can work together. Yeah, over to you, Manoj.
Thanks, Parani. Thank you. And there have been some questions on the chat, Parani. Since I am controlling the screen, I was not able to answer. Maybe you can start off answering it. Okay. Super. So I think that was a batch of information on nanometric and microscopic stuff. So probably if you have questions and we can always see them in action, you're welcome. And now we just want to jump into a kind of a topic which is very useful for people who have printers, who are into additive job shops and things like that. So we have a certain advanced print parameter choice, selection or qualification. That is when you have a new powder coming in, when you have new part to be printed, there is always a challenge what kind of parameters you set, which we have discussed with Ms. Akshita and Mr. Suhaib a few times. So one of our topics, which is a solution, additive manufacturing solution called Versus, is actually to understand these areas, to help you in these areas, into alloy developments, if you are looking for comparing 2, 3 printers, which printer are the printers equal? Even though the even though the brand, model, everything could be same, even the parameters could be same, but they may have inherent differences. So you can understand them. You want to understand which kind of scan strategy is good. If you want to calibrate the laser, if you want to do a build envelope qualification, which part of your printer is behaving in a nice way, or good enough for your part. Good. Sometimes you don't need always the best print. You need a good enough print sometimes. You want to increase your print speed. So these are some of the areas which we can attack by this methodology called Versus. Versus is actually a brand name or our name. Basically, this stems from one of a patent, what we have generated. The topic is listed there. You could probably, look into this. It is available as a free topic in the internet. And this is to enable rapid X-ray CT characterization for additive manufacturing, and then to arrive at the parameters in a very, very quicker way than what you do today. So how do we achieve this? Is we request you to print out this kind of artifact. I think many of you might know this artifact, which is a combination of a cylinder combined with different, print materials like tapered or narrow fins and so on. So these, when you print this artifact with a set of experiments, then we are able to give you a certain kind of information which will enable you to get faster. All the features what we mentioned in the previous slide will be possible with this method. You make your own design of experiments. So for the batch of 80 parts, you would decide which coupons have which kind of print parameters. So that is a design of experiments which you would do. Then you would remove all the artifacts and ship it to Zeiss. We put it in a CT machine. I will explain you a CT machine in the next video. We put it in a CT machine, and then once we measure it over a few days, we are a few days or about 12 to 14 hours, we are, depending on what you want, what kind of porosity you want, we are able to answer a few questions like, how is the deviation from CAD for dimensional accuracy? How good is your machine? How is the segmentation of pores and cracks? And then you get a lot of interactive reports as to, I mean, I think you as a builder would really, you can see a wealth of information. This is one of the data sample. You have volumetric energy density, which you have categorized on different parts. And on the vertical column is the relative porosity between these samples. So we are then able to give you a visual topic that okay, the part which was worked with a volumetric density of 90 and with certain other parameters is having a very, very high porosity content. Probably you printed it very quick, but it is having a porosity content or the material is not fused properly. Whereas a certain set of artifact is having a wonderful porosity content, is green all over with respect to dimensions. So then you know that when you want to print some critical areas, you would like to use this set of parameters. A similar way, you are now viewing the data set with reference to velocity and power and porosity. Again, it gives you a data that when you go up on the velocity, then you don't have fusion. When you go down and then on velocity, but you go up on power, you have probably more keyholes. And there is an optimal level somewhere in between. So you get a visual representation, which what we are told from the guys who have done the patent from our companies, this process normally takes a lot of time. And with our patented technique and the CT, what the X-ray, what we use, we are able to do it at a much faster rate, right? So also then we give you more information on how is how is the porosity. In this case, we are looking at the XY position and the porosity content. And also there is a relation to which feature has been printed, body or the certain fin, the fin with a 0.5 millimeter wall or a fin with a 3 millimeter wall, though they can behave differently. And then different inclinations and different cylinders, how they have behaved with reference to the parameter set what you have used. So this is a kind of advanced technique which we can interact. Any of you have such a need. We know that the market is moving in the direction of printing additive parts into kneecaps and so on, into aerospace. There are a lot of serialization topics which are going on. We would like to support you people. Coming back, there is one last section. Among this, we will go a little bit deep dive into the tools, just to get you an idea how these tools can work together. There is data from different sets can be mind-boggling unless you put them all together and then you start seeing patterns in them. So that is what we will do. You may know most of the tools. If you don't know, you're welcome to our office. Right. So one of the topics, the first topics which comes to a 3D printer is reverse engineering. We can do reverse engineering using many of our tools. Normally, you do it with a scanner. We can do it with a scanner, but we can do it with a CT. In CT, you don't only reverse engineer the outside of the part, but you reverse engineer the insides also. So that's an advantage what you have. You can also use a CMM. And once you get a point cloud data, then you can import the point cloud. And then we have a reverse engineering software with which you can fill in some voids, do what is required to create it into a CAD model so that, you are able to then give it to the slicing software for your printing functions. This is one part of it. The second part of it is it has a tool correction option, because normally what you print is not what you want, at least in the first iteration. So how do you get to the final part and how do you reduce the number of iterations? That's a challenge. So we have a tool correction, which is a tool correction function when it comes to a conventional mold, but also you call it tool correction for additive manufactured parts. So what we do is, okay, this is the typical step of optical 3D. You acquire the data and then you move on to reverse engineering. Yes. So this is a tool correction function. So when it's more required in additive because as you keep heating up the layer on top, there is a warpage which forms at the bottom. So what comes out is not what you desire. So what happens is there is a CAD model of the part, and then there is an actual part which is getting printed. There is a deviation. So our software negates the deviation, inverts the deviation, puts it onto the corrected STL CAD model, and then you are able to do an iteration, which is much faster. So this is a methodology. We have guys working here who can do this, who can work with you to see how we can make it quicker for you. Some examples are shown here. This is applicable both for metal and for plastic. Some more topics around model compensation. This is a success story with a company called Q-Tech Roding in the US. I'm going a little fast just to make up on the time. Right. Now comes a key topic, important topic. Let's please wait for the next 5, 7, 10 minutes. Why computer tomography for additive manufacturing is to identify, inspect. Inspection is common. You may do inspection with a 2D X-ray or 3D X-ray, but we can do metrology. That's what is important today. So you can look at inclusions, you can look at cracks, delamination. You printed a part, but you want to know what's inside. What's going on inside? Is the part good? Good to fly? That's a key topic today, good to fly or not. So, and particularly with the additive topic. So you can understand a lot of analysis if you put a subject a part to a X-ray measurement, right? So in order to explain, I think it's good to see a video. Let me take you through a video. Just a minute, I will, yeah. So please assume that this is an additively manufactured implant. Now the gentleman comes to our Carl Zeiss office and he says he would like to inspect this part and he wants to know what's inside the part. Is it good to go on the patient?
Manoj, you can speak while it is moving because the video
Okay.
was.
Understood. Understood. Right. So let me speak. So as you see here, the gentleman walks in and he is putting the part on the. You just have to place the part in a seat. You don't have to do anything. No pre-processing, nothing required. Just put it on the CT. And then, you need to set some parameters like print parameters. There are CT parameters which should be set. And then I will move on. Yeah. Then you have to push the button, then the window closes, and then you have X-rays passing through the part, collecting all the data, about 3,600 orientations of the part. The part gets rotated. Then you collect orientations of the part, then combine all of them. So when you take a 2D picture from your camera, so you call it pixel. So in this case, this becomes a three-dimensional pixel, which is called voxel. So you are able to completely, you have reverse engineered the part in a span of say 30 minutes roughly. So you reverse engineer the part, you know every voxel in the part in with a resolution of roughly about 30 to 40 microns. We can go down up to 5-7 micron, but that involves giving it more time, giving it more energy or less energy, depends on the material. Then you get a picture like this. So what you see here is a 3D data, but they may section it. As you have seen, they have sectioned it out, and they are looking at how is the part inside, how much is the kind of porosity, what is the location of porosity, will the porosity be visible when you machine it, because you need to probably do some post processing. So you can see that we are able to measure the voids, cracks, and we are able to represent it in a very nice way for you to look at. This is the power of a city, that you can see a lot of things. And then what all you can do? Of course, you can do a visual inspection with part by part, layer by layer, you can go in. As Pioneer was mentioning, you can do it slice and you will know, okay, this was slice number 32 of the manufacturing. So you can correlate over there. You can do metrology. So you don't need to use a CMM. You don't need to use a 3D scanner. You can, what all you can do here? GD&T inspection. You can do dimensional, positional, run out, and actual nominal comparison. Wall thicknesses. Do you need a thick wall or a thin wall? Is it warping? Because after post-processing, after the heat, is it warping? Trend analysis. Full surface inspection of internal structures. Point by point measurement. Yeah, it's possible to do every single point comparison on critical areas. Also, defect analysis according to different standards can be done. You may probably look at this. I don't want to read out everything. Voids, cracks, gaps, and so on. What is critical is this. You may know X-ray as a machine which can just give you image. But today we are talking about reproducibility. That is, you can subject it to repeatable measurement. You don't need a CMM. I'm repeating it. We are a CMM manufacturer, but I'm repeating that for many kind of tolerances, you don't need a CMM. And as you can see here, reproducibility is in the order of 2 microns, which is absolutely amazing. So this is the power of combining voxels from using the software, and then creating the edges internally, which is a critical topic here, and then applying metrology and GD&T. So we will demonstrate. So how much can you penetrate? This is a key topic in SCT. Plastic up to 300 millimeters, aluminium 200 to 220 millimeters, titanium up to 100 to 150, steel up to 30 to 40 millimeters. They are cumulative wall thicknesses, not the size of the part. The part size itself can be 300 cube, 350 cube, or even 500 cube actually. Okay, so as I told you, we were using AI. So we have a lot of applications built around this. We have automatic segmentation, that you have repeated serialization of parts. You can use AI for automatic segmentation, automatic defect detection, and evaluation, and then reporting. Then multiple parts can be put together, cavity number with a cavity numbers, to know which cavity, you can correlate it to cavity. This is in case of injection molding, by the way. Right. So some examples of a part of a piston, which you saw in the first video. That piston is now, we are looking at the piston, we are seeing a crack, and then we are going a deep dive to see why is the crack originated. The normal methodology is you look at, like, if you, God forbid, you go into a hospital, it's possible that they will do a complete scan of your leg or arm or whatever. And then the doctor would look at and then say, yeah, can we do a rescan on this ROI area? That's what is done here. You do a CT, then you look at that, okay, there is a crack I can see at a certain location. Can I do a finer measurement at 18 microns? Oh, now I see it in a little more detail. So can I get a little more higher resolution to see what is going on there? Then I go down to 11 microns. Fine, good enough. Now, can I cut it and put it in an X-ray? Why has it cracked? What you see here now is a highlight or a material with a white spot. That white spot is a foreign body which has come in there. So that foreign body, we will have to confirm what is the contamination particle in a microscope, as Mr. Parani explained in his presentation. Now, one case study on a B-52 bomber, very relevant probably to today to what is happening around the world. So we have to keep it flying because there is a fuel-cooled oil cooler. One of the supplier had probably died down, and this is a case study which we worked at ORNL. And we don't have a drawing, or we have a drawing, but we don't have the tools, and the supplier is no more. So this was 3D printed. This was 3D printed, and you can see the complexity. There are a lot of cooling channels. Some are cold fuel and some are hot fuel. So, they have to mix, and the heat has to be exchanged. So there are a lot of channels, internal channels. How do you confirm that the part is good when there are a lot of internal structures? You cannot cut every part. I mean, it doesn't make sense. So this is where it was printed in 3D. A part was cut out, preformed, or you do the little bit of post processing to take it out, and then we use our tools, which we have seen in various slides. We use all these tools, and now you will see a fleeting display that this part is getting measured on a CMM to measure all the outer dimensions. Then it is subject to a scanning methodology, where we scan the part to understand the form, and then we put it in a CT, as you saw in the previous day image video. Just put it in the CT, and then the X-ray takes care of it. The part keeps rotating, and then we collect all the data. The part will be moved left and right depending on the magnification you want. It's absolutely like a cinema theater. The technology is very similar to what you see in a cinema theater. Then you put it in an XRM because you need a super high resolution CT. So that's what happens here. The gentleman is putting the whole part, as you can see, in an X-ray microscope, but we focus on a certain location. We don't measure the complete part here. We focus on a certain area which we feel is probably the problematic area. And then, okay, we have to subject it to the metallurgical tests in a microscope. That is what you see here. And then the requirement could be that, yes, you need to finally take a sample and put it under an electron microscope. So there is a destructive test which will come now on the electron microscope. So this is a series of activities what go on. Now, what is the result you get? You see the result on the left. The outer dimensions have been measured and compared with CAD. Green is good, blue is okay, red is parts which need to be worked upon. And you also see the internal channels. What do you see in the internal channels? You see a lot of dimensions. You see the diameters, you see the positions, the width, and also you see the wall thicknesses. You see a CAD comparison of the internal channels. You see a cylindricity deviation from the internal channels. These are all absolutely essential because they're high pressure fluid moving around, and you need to know this data to see what is the effectiveness and how it is gotten printed out. What you need to correct to see that the channel is not having unburnt powder, these kind of stuff which is blocking which is reducing the pressure. So, and what is the kind of roughness inside cooling channels? Roughness inside parts which are printed, which are critical. So this is what Parani explained already, that roughness of internal channels which cannot be seen can be measured. Similar example of a copper feature. Internal roughnesses of the copper feature are getting measured, probably used in some nuclear fuel applications. What is the final result? The final result is you see a wonderful outer data. You are happy with it. At least you get an idea what has gone wrong, what is right. You see some red, green marks. So you know that it's relatively fine. But what is inside? Okay, now I'm slicing it through and I'm looking at only the channels. Are they good? How are the cylinders? How are the circles? How are the diameters inside? What are the positions? And how are they formed? Are they parallel to each other? And then now we go deeper into the resolution. We see that, okay, there are some areas where probably the material did not get burnt properly, or there is a contamination. Then we improve the resolution to see a very fine structure. You can probably look at the structure, what your printer is giving it. And then you move on to electron microscopy, where you look at it at 150 nanometers. But what is important here is the seamless view from a macro component to 150 nanometer resolution. See, this is technology. So this is what is possible. And then you have the structural topics getting the microstructure getting revealed by the EBSD of the electron microscope. So this is the kind of, you know, data sets what we can produce. That is point number 6. That is, we are able to give you a set of process data measured at various levels using various technologies, but grouping them together. So this is what we wanted to present. As a summary, we looked at the powder and then the different characteristics, what we can do in a powder. And then we looked at some advanced techniques. Then we moved on to CT and simple measurements, what you can do in a different equipments.